we want to sort of share with you. This is a project that myself and Peter Muka and Dan, there she is, are the investigators on. It's funded by the National Science Foundation. And it's our attempt to try to pull a lot of these pieces together. So I'm going to go ahead and just show what this is. Let's get the slide to work here. There we go. I'm recording. There we go. All right. So there we go. So we're effectively calling this IdeaNet. This is this is where, it's the trick for getting grants is to make sure you have a good acronym, and ours was integrating data exchange and analysis for networks. That's what IdeaNet stands for. And that really is exactly what we want to do. This is a project that was developed with funding, or is being developed with funding by the National Science Foundation through their Human Networks and Data Science Infrastructure Project, or the HNDSI, or we refer to colloquially as HANSI. So it's the HANSI project, and we have four main goals with this project that have to do with trying to secure and save the history of network sort of analysis data that's been collected for so many years, but do so in a way that is profitable for future investigators as opposed to just being an archive. So that involves, we think, four basic steps. The first one is we're building a secure network repository, excuse me. And the point here is that we're routinizing the capacity for archiving network data, including sensitive and secure data. And I'll explain what that means in a minute. But that is, we want a way that for people to, once they finish their study, a good social networks and health kind of study is going to have lots of rich network data in it, but it's also probably going to have sensitive data or private data of various sorts. We want to be able to share that in a way that recognizes all those kinds of constraints. We want to build a network translation engine. I should actually be a little more accurate. We have to build a network translation engine. Not sure if we want to, but as you're going to see in a minute, there's lots of different network formats, and so we need a way to play with that. So once we have those two things, we have some data, we have it in a format that's usable. We'd like to make it so that it's more usable for people in general. And so to do that, we're essentially pre-computing a lot of the scores that you might otherwise think you want to compute. And our thinking here is that this broadens the base of users for people who might know substantively or logically what they think about network analysis, but don't know technically how to do it. This would make it possible for them to use these data in a way that is both profitable and much less error prone than trying to learn how to do it on your own or on the fly. And which goes hand in hand with that is we're developing a new software tool to help visualize and analyze networks without having to go through as much of the data cleaning process that Gabe was just pointing out. I'm probably going to go through these four elements just one at a time and show you what we have. And so you think that the reason we're sharing this now is that we're in the second year of the grant, what will end up being a 4-year grant. And so now we're at the state where we can really use people's advice on what they want us to include. So as you're going to hear me describe what we think we're doing and sort of what we've done thus far. And I'm doing that with the hope that that triggers in you a desire to ask for something that we can, sort of a feature list that we can add and make it work. So just to set it up, the first point is this data archive. This is, of course, recognizing there are plenty of great archives out there. If your interest is in doing network science, that is within that sort of third branch over there where you're looking at the properties of large-scale networks, there are a bunch of network repositories out there. Almost all of these are open source data and just the graph data. So they're usually almost just an edge list. Sometimes is a different format, but essentially there's no other covariates to go with it. So you might have, for example, the ad-health-romantic sexnet, but you don't have any idea who's who in the network. You just have the literal edge structure of that network. And we think that's usually suboptimal for most substantive researchers. So people who want to understand network analysis, who want to do network analysis with an eye towards learning something about health or health behavior, for example, you need more than just the graph structure. You need the graph structure and the covariates that go with it. And this, of course, fits in just timely with the fact that both NSF and NIH have new data sharing policies that have become data sharing requirements For anybody who has an NIH or NSF funded data collection effort, you have to store and archive that data. There are certain thresholds that are going to get introduced over time, depending on how big your grant is. Right now, if your grant's under 500,000, you can hide your data for a while, but that's going to go away eventually. We think rightly, the public has paid for these data, and so the public should be able to use them as a general sense after investigators have gotten their chance to use them for their initial purpose. And I think that's good both for from a tax, using people's funds standpoint, but also because most of the time investigators rarely mine all of the gold in a data set. There's usually a lot there that's really interesting, particularly if you can compare it to somebody else's data set in a similar way. And so having a full archive of data on social networks and health, for example, will make it possible for the NSF and the NIH to get a much greater substantive return on their investment in data collection by allowing all of you to use these data in a way that would otherwise be difficult to do. But currently that's really hard to do, so we're trying to build that. So the way we have in mind, our vision for this, is that there are essentially two categories of people, right? There are people who give us data, and there are people who want to use data. We're calling those depositors and clients. Depositors, the goal is that if you're in the process of collecting data and analyzing data and doing the grant, I promise you didn't build into your funding creation of a public use data set with fully documented and comparable to the other data sets that are out there. Most people just don't have time to do it, and so they meet the letter of the law for these kinds of depository things by saying, email me and I'll send you a copy, or just dumping it raw into some kind of an archive or some such with minimal processing and minimal metadata. This is because depositors just don't have the time. They don't have the resources often to do what's necessary. So what we're trying to do is to build a series of filters and web forms that minimize the amount of effort it takes to go from the data you already have as an investigator to the data you'd like to share with the world. And so the extent to which we can simplify that process, the better. One of the key elements here is that we're going to have a fully IRB compliant server system. And that is that as a depositor, you decide what the restrictions are on your data. So it could be as strict as ad help that has to be used on a particular kind of machine in a particular kind of environment or something like that. Or it could be as easy as, be nice, don't do something evil with the data, right? And so that's up to you as a depositor. You say what you want, and then we make users attest to it if they draw out the data. From a client standpoint, the key is that you're trying to think what you want to write your dissertation on. You think it has something to do with networks and health. Maybe you're interested in obesity and smoking, and so you'd like to be able to search into a database, networks, obesity, smoking, and see everything that comes up. And so that's our goal, is we're going to leverage the Dataverse, which was initially started at Harvard. There's a new branch of it at UNC, and we're opening a Duke branch here any day now. And there's a series of tools called the Impacts tool that allow you to interface with Dataverse and get all of the searchability and metadata and archiving tools that come along with Dataverse, but also keep it under a secure compute environment. The other side we want to do is that we built the project looking forward, but we also want to, as best we can, look backwards. There's been 80 years of network data analysis that's occurred, and a lot of that data is still existent on somebody's file server somewhere, the back of a dusty drawer. And so we're hoping to be able to fund some of the collection of that data. So if any of you, particularly graduate students or young professors, have advisors that collected some of this data, and it's sitting on a floppy disk in the back of some folder somewhere, tell them to send me an email, and we'll get those data ready so that other people can play with them. So that sounds like a big promise. How does it work? It works through this process called IMPACT. And I forget exactly, maybe Peter remembers, I forget exactly what the acronym for IMPACT stands for. But effectively what it means is that there's this little bundle of software tools that sit behind Dataverse. And what these things are in the computer world known as a notary service. These are things that filter through requests and promises or passes that people make with the data. And what's nice about the IdeaNet data cert is that it was built entirely around the Dataverse storage system and management system and metadata service. so that it's possible to have all of the metadata that comes with the data set, the number of observations, the variables, and all these kinds of things, as well as the data description, code books, what have you, be readily searchable and available for anybody who wants to find them, but all of the actual secure data held in a secure data archive. Then when the researcher that's interested in using those data comes and finds the piece they want, they read through a little checklist of the things that's required to use that data, most basic of which would be that your own IRB gives you approval to use it and agrees to the terms of the data burst of the data use agreement, which would also be a web check form. And once we get a certification from your IRB that that's true, you get the keys to the real data. And there's some other sort of magic behind the hood. It's possible that, for example, a depositor could require the data to only be computed on the server, so you would never actually get a copy of the data. We're not going that far, at least not in the first iteration, so there's going to be some data that we probably won't be able to use if people have that strict requirement. But I think most of us, what we want to be reasonable is to say we've collected these data, we promised our respondents that these data would be held securely, and that people would be using it for the benefit of society, and that it wouldn't be shared widely with the public at large. And so long as someone's IRB is willing to certify that that's the case, that the person is willing to do that, then we're happy to share the data. And so for at least a large class of data, we think this will be possible. Now, of course, if you have completely de-identified data in a sense that it's open or what have you, then that's even easier. We don't have to do any of that. Your data use is just, be nice and don't try to make a bunch of money or something off it. But that's the kind of thing that you as a depositor can decide what you're going to do. Now, the problem is if one of your goals is to take the data as people have sent it, then you have to take the data as people have sent it and turn it into data that people can use. And it turns out that there are a lot of network data formats. This is a list of the most common ones that we were able to find. And there's something like 30 different data storage formats, ranging from simple text files to things that are really complicated nested data structures. So at the end of the day, what we're doing is we're starting with the simplest things first, and then some of the common legacy tools such as UCINet and Gephi and things like this. And then we're going to build the tools to translate out of those. And then ultimately, as we get deposits from more and more of these formats, we will write a script that allows us to translate from that into the base R formats that we're using now. But this just gives you a sense, especially those of you that are new in the field, that there are a lot of different network formats out there. And our goal is to simplify these as best we can. And we do that because it turns out that almost every data set eventually is going to be some combination of an edge list and a node list. And so even if you have a really complicated multi-layer dynamic network, valued network, that's really just a series of labels that go on that edge list. And so at the end of the day, what we're turning all these complicated data structures into is an annotated edge list. It's an edge list that has other attributes such as value and timing and relationship type and layer or what have you, so that it's possible then for all to ultimately get stored in the same way and processed through in the same way. Once we have that, we want to make the data as useful as possible for people. It would be nice that if you're a user and you care about smoking and obesity and you think that maybe people's peers affect their smoking, to be able to pull something like a peer autocorrelation measure without having to know how to calculate it. And so we're doing lots of pre-computing. And so every data set that goes into the repository will have a series of metrics computed on it. We're calling these our core compute metrics. And the core compute engine generates, for now, a series of basic node level measures and a series of network level measures. And it would be interesting hearing from you what kinds of measures you think those would be most useful, because that's where we're going to ultimately go. So how does it work? It really is a single function, right? So we'll have something like the IdeaNet utilities. One of the base functions is just reading in the data and writing it out. So we call that netWrite. And you can see what it looks like. So it ends up being, we're saying in this case, the data is a text adjacency list. It's not these other things. It has some names. It has some attributes to it. We run through and do our process. And when it's done, it just spits out these results. And so it's kind of a nice way to get them in the sense that it gives you everything that we think is probably that most people would want to know about their network off the set. And really kudos to John and Tom for their first draft on building this tool, because it really is quite impressive. It comes with some automatic reporting functions, including graphical reporting on the system level measures. And similarly, you get the same thing on the node level measure. So this is a relatively small network, but you can see you get a whole host of different measures that have to do with what that node's position is in the network. We haven't really talked about a lot of these, but you get the classic centrality scores, you get them weighted and unweighted, you get Ron Burt's hierarchy and constraint measures, you get some ability to reach other people quickly or not, things like that. So this is, again, one of these things that we're asking your help with. What are the kinds of indices you would like to see added to the base compute engine that would go for every data set that is put out there? And again, the report automatically gives you a series of visual reports to help you see what's there. But when it's done, it also gives you all the data objects. Now, one of the other pieces that we've added to it, in addition to the node metrics, because our team is particularly interested in community detection, is that we've started a routine that just does all of the community detection. So as you'll learn when you hear Peter's piece, there's a lot of different opportunities for community detection. Some of them are great, some of them are bad, but right now, at least one of the things we're doing is just letting you see what they do. And so this is the off-the-shelf best or most common community detection routines applied to whatever network we happen to have. And in this case, we're doing about 8 of them, it looks like, or 10 of them, it looks like. So it ranges from everything from the really slow, but usually quite good one, edge between this, up to really fast, but perhaps not as good, stochastic block model and everything in between. So it's a lot of work under the hood to go through and make sure that this happens. We're not arguing that this is the optimal way to do community detection. It turns out that that's a really hard problem, and we have some, we think, better answers for how to do that. Peter and his team has developed a remarkable set of tools for identifying the range of possible answers that are available for this problem. But in terms of getting something quick off the shelf, it's better to at least see what the variance is as opposed to see nothing. So that's what's there. So that's all under the hood, and we thought, well, you know, if we have all of this and you're going to make it available to people, why not go one step further and make it possible for them to use it in a way that doesn't require them to know all of the data wrangling stuff that Gabe was just teaching you. And so to do that, we've developed this thing, a Shiny app called the Network Visualizer with IdeaNet, which is a point-and-click GUI interface for graphical user interface for people who are interested in using network data, but without having to do all the R programming. So if you don't want to learn R off of that, this is a way to at least get a start with it. And we're doing it now as a Shiny app that would be run local, but the hope is to be able to perhaps make this run on the secure server, so that you could, for people who do have data that they can't share, they might be able to still get some information, answer some stuff out of it. And it works really quite nicely. And again, Tom and John and Ethan, I don't know if Ethan was able to make the call today, but Ethan's an undergraduate here at Duke who did the first draft of the programming on this tool, and I think it's come out quite nicely. It really is a classic Windows kind of interface. You load some data, you load a nodes data set in this case, an edge data set, you pull them in. As soon as you pull it, it looks like a spreadsheet. You see what the data set looks like. In the processing set, you can decide, you can tell it explicitly which column in the data set has your node ID. It doesn't have to be the first column. It doesn't have to be the second column, right? You can say what label you want to use, and that can differ from your ID or be the same. You can color it or you can size it depending on what you want, and you can move back and forth between these in the visualization. Same thing on the edges. You tell it which column is the sender and which column is the receiver. You'll notice in this case that it's not the first two columns, right? You tell it which is the value of the network. In this case, we do tell it later that values are frequencies. I forget where that was at. I might have just cut that out. But in any event, we tell it what the edges, what the edge values mean, and then you can visualize your network, right? And so for people who want to do that initial exploratory data analysis, it's really nice. And you can use, we have all of the iGraph basic layout functions are here. This just happens to be the Puchman-Rheingold layout. But you can do lots of different sizing and things like that with the data. And when it's done, you get out a report on that data set and the network metrics that are there. And saved into your environment is a new data frame that includes all these measures, which you can then merge onto whatever substantive variables you care about if you want to predict smoking or behavior. So, the tool is pretty clean. It works fairly nicely. It's a Right now, it is bare bones. Like we are, you are seeing the beta version of this. And so the reason we're sharing it is we would like to get your feedback and help. So I'm going to stop there and see if people have thoughts or suggestions. So thank you. Moving on. Right. If anybody has, I did use most of the time. If anybody has questions on this tool, if you'd like to help us test it, send me an email. And I'm happy to sort of share earlier versions with it as we get them going. In particular, if you or any of your colleagues have data or in the process of collecting network data and you're facing this network data archiving wall that you're about to run into at the end of your grant, please let me know because we would like to help you get those data in a format that can be shared in a way that protects your respondents and also meets the open science goals that we all have for making the world better.
There's a question in the chat, Jim.
Okay, where is that? Would it be possible to get a list of what's currently included in the measures? Yes, that has not been shared anywhere else yet. Currently what we have are, I had it up there on the list, but I'm going to read it out loud here without trying to reshare my screen. I think it'd probably be the easiest. Currently on the node level, we have essentially a bunch of centrality measures. So we have in degree and out degree, in strength and out strength. That's the weighted version and the unweighted version. We have closeness centrality, betweenness centrality, eigenvector centrality, and Bonasich centrality. Bonasich centrality has that weight to it. We've arbitrarily picked the 75th percentile on the weight, so that gets you not the full range of others, but the sort of the intermediate range. And we have both the positive and negative weight for that. We have all three of Bert's structural hole measures, so eigenvector, constraint, effective size, and hierarchy. And then we have a diffusion reachability measures. We have the number of people you could reach in the network, the number of people who can reach you, and the joint of that depending on how you treat the directionality of the edges. At the system level, we have strong and weak components. We have, what else do we have here? And strong and weak components. We have the basic description of the number of ties and edges and tie types. We have the dyad census. We're going to add probably the triad census. We have the clustering coefficient. We have the average path length, and we have pairwise reachability, both strong and weak, depending on directionality. So those are all things that are there. Katie, well, you don't currently have access to this tool. It is a little bit raw. You are literally the first people in the world outside of our research team to see this. This is its debut. So if you'd like to see it and play with it, again, just send me a quick note and we'd be happy to share and get your feedback. That would be awesome. Questions or thoughts? Again, if you have suggestions, if your favorite metric isn't in there, one of the things we're going to be doing is really fine-tuning. So the next thing on our agenda is to fine-tune the community detection one, and also then to add some basic role detection stuff. So it'll have both of those. And then anything else that is on your list is stuff that I would love to hear. All right, Peter, Dan, anything to add from the PI teams list?
No, I think that was pretty solid. Thank you.
All right. Great. Let's take 5 minutes then, and we'll come back with statistical modeling for networks. We'll spend the rest of the afternoon essentially talking about that, and then finish up with network visualization. 5 minutes. So let's start at 2:35.